Hello everyone. Today we will be talking about GUI with Qt. So we are going to move away from console programs and start building graphical user interfaces. From now on, your programs won't just print text in the terminal. They will have windows, buttons, menus, text fields, and all the things you normally expect from a computer program that runs on your desktop. So, up until now, almost everything we have written has lived inside a console window. We type something, press enter, and our program responds. That's a perfectly good way to learn C++ because it lets us focus on the language itself. Real software actually doesn't work like that. Think about the applications you use every day: your web browser, your file explorer, Spotify, Discord, Visual Studio Code, and etc. etc. None of them asks you to type a command into a terminal. Instead, you click buttons, you drag windows, choose menu items, and interact visually with your keyboard or your mouse. The visual layer is called the graphical user interface, or simply GUI. You could pronounce it as GUI or GUI, both are correct. Today we will simply call it GUI. A GUI makes software much easier to understand. Instead of remembering the commands, they simply click on buttons or the menu options or however the software is designed. But of course, for us programmers, building graphical interfaces adds another layer of complexity. Instead of just focusing on the logic of the application, us programmers now have to build whatever the user is going to interact with on the screen. So fortunately, we don't have to build all of that from scratch. That's why frameworks like Qt exist. Before we look at Qt itself, we need to understand something much more important. The way a GUI application runs is completely different from the console applications that we have been writing so far. Think back to one of our earlier C++ programs. Execution always began inside main. The program executed one statement after another. Maybe it printed something, maybe it asked the user for input using standard cin. The user then entered some data, the program continued, and eventually the main finished. Everything happened in one clear sequence. We often call that procedural or linear execution. Now compare that to a program like a web browser. When you open it, does it immediately close? Of course not. It opens a window and waits. Nothing happens until you do something. You click a button, you resize the window, you press a key, you receive a network message, and the application simply reacts. This style is called event-driven programming. Instead of constantly asking, "What should I do next?" the application waits until an event happens. Qt is entirely built around this idea. The modern desktop interfaces follow a design model called WIMP. Each letter here represents one of the building blocks of graphical user interfaces. The first letter is Windows. Here, the concept is that a window gives an application its own workspace. You can move it, resize it, minimize it, or place it inside another application. The second letter is Icons. Instead of reading long commands, users recognize pictures almost instantly. A small trash bin icon is much easier to understand than typing a delete command. Next comes Menus. Menus organize commands into logical groups. They help keep the interface clean without filling the entire window with buttons. Finally, we have the pointer. Usually that's your mouse cursor. It connects your physical movement to objects on the screen. You point, click, drag, and interact directly with the interface. Now let's meet the framework that we will be using throughout this lecture. Qt, pronounced as Qt, not Qt, only Qt, is a cross-platform application framework written in C++. Normally, if you wanted the same application to run on Windows, Mac OS, Linux, you would need to rewrite large parts of the software using different operating system APIs. Qt solves that problem. You write your interface once using Qt classes, then Qt handles the operating system specific details underneath. The same application can run on Windows, Linux, Mac OS, Android, embedded devices, and other platforms with very little modification. Another nice advantage is performance. Qt applications compile directly into machine code. That means your application isn't running inside a browser or a virtual machine. It executes directly on the operating system, so it provides excellent CPU and GPU performance. Before we start writing code, I think it's worth spending just a minute looking at where Qt came from. Qt actually has a long history. It was first developed in 1991 by two Norwegian programmers. A few years later, they founded a company and Qt was released publicly. As Qt became more mature, it became the foundation of one of the most popular Linux desktop environments, KDE. Later, Nokia acquired that company and invested heavily in Qt for its smartphone platforms. Eventually, the ownership moved to Digia, which later established the Qt company. Today, Qt is widely used in industries far beyond desktop software. You'll find it in automotive systems, medical devices, industrial automation, embedded systems, and many commercial desktop applications. Qt has been used in commercial software for decades, and you'll find it in products that millions of people use every day. For example, Adobe has used Qt in some of its desktop applications. Autodesk relies on it for professional engineering and 3D animation. Tesla uses it for those interfaces inside the car and for those large screens. And Walt Disney uses it for animation pipelines. VLC Media Player uses it, which is one of the most popular media player in the world. Now, these are very different applications. Some of these are creative tools, and some are engineering software, and some other is running inside cars. Yet, they all use the same framework. That flexibility is one of the Qt's greatest strengths. Now let's start looking at the building blocks of a Qt application before we start coding and everything else. The most important class we will encounter is QWidget. You can think of a widget as any visible object that appears on the screen. Forget what you know about widgets in smartphones. Those are used in different contexts. Here, a window is a widget, a button is a widget, a text box is a widget, a label is a widget, and so on. Even many containers that hold other interface elements are widgets. Because they all inherit from QWidget, they automatically share common functionality. Every widget knows its size, it knows its position, it can be shown or hidden, it can be resized, it can be styled, and so on. Qt organizes widgets into several broad categories. Containers such as QMainWindow and QDialog are used to organize other widgets. Display widgets like QLabel simply present information to the user. Input widgets such as QLineEdit or QComboBox allow the user to provide information. And finally, button widgets trigger actions when the user interacts with them. Earlier, we said that GUI applications don't simply execute line by line and exit. Now, let's see what actually keeps them alive. At the heart of every Qt application is something called the event loop. The operating system is constantly monitoring what's happening. Maybe the user clicks a mouse, maybe they press a key, or maybe a network message arrives. Whenever one of these things happen, the operating system creates an event. Qt collects those events and places them into an event queue. If an event is waiting, Qt delivers it to the correct object. If nothing is happening, the application simply waits. This process continues for the entire lifetime of the application. Your application isn't continuously asking whether the mouse was clicked. Instead, the event loop delivers that information only when something actually happens. That's one of the reasons why GUI applications remain responsive without wasting CPU time constantly checking for user input. Okay, this is probably the single most important concept in Qt. Everything else builds on top of it. Qt introduces a communication mechanism called signals and slots. Imagine you have a push button. When the user clicks it, the button doesn't know what your application is supposed to do. Its job is simply to announce that something happened. That announcement is called a signal. A signal contains no application logic. It simply says, I was clicked. Something else must decide how to respond. That's where slots come in. A slot is just a normal member function that performs some action. Maybe it closes the window, maybe it saves a file, maybe it updates a label. But Qt connects these two pieces together using the connect function. The button emits a signal, Qt forwards that signal, and the connected slot is automatically executed. One signal can trigger several different slots. Likewise, several different signals can all trigger the same slot. You'll use this pattern consistently when building Qt applications. Now it's finally time to begin creating our own Qt applications. Before today's lecture, you should have already followed the instructions provided on Moodle and installed Qt Creator. Inside Qt Creator, creating a new project is quite straightforward. We choose File, then New Project, and then Qt Widgets Applications, and then let's give it a name, let's say App Example, and let's choose a location. Then Next. For now, the default names are all right. Next, and finish it. So here, as you can see, Qt Creator is generating the files for us. On the left, you will see the directory structure of your project. Here you will have header files and source files. Under header files, you will see mainwindow.h. If you double click it, you will see the file here, and then main.cpp, and then mainwindow.cpp. Don't worry if some of it looks unfamiliar. We will go through everything one by one. Now that we've created our Qt Widgets project, let's look at the files that Qt Creator generated for us. Mainly the source files, which are main.cpp and mainwindow.cpp. Let's begin with main.cpp. Just like every C++ program we've written before, execution starts at the main function. The difference is that this main looks a little different from the console applications we've been writing before. You'll see several unfamiliar classes here and there, but don't worry, their jobs are actually quite straightforward. First, Qt creates a QApplication object. This object represents the entire application. It communicates with the operating system, receives user input, manages windows, and prepares everything needed before our interface appears. Next, we create an instance of our own main window class. At this point, the window exists only in memory. It hasn't appeared on the screen yet. And that's why the next line calls show. This tells Qt to make the window visible. And finally, we call the execute or exec. Remember the event loop we discussed a few minutes ago? This is where it begins. Once this function is called, the application starts waiting for mouse clicks, keyboard presses, timers, and every other event that happens while the program is running. You may also notice the argc and argv parameters. These are the same command line arguments that ordinary C++ programs receive. Qt simply forwards them into the QApplication object in case they are needed. Now let's move into the file where we will spend most of our time. This is mainwindow.cpp, which is right here. So let's look at the code. The first function you will see is the constructor. The constructor runs automatically whenever our window is created. The first line calls the constructor of QMainWindow. That's something you've already seen in object-oriented programming. Since our class inherits from QMainWindow, the parent class needs to be constructed first. Next, you'll notice a pointer called UI. Qt Creator generated this pointer for us automatically. The call to UI setup UI is one of the most important lines in the entire project. Qt Creator lets us design interfaces visually. That visual design is stored separately. When this function executes, Qt reads the design and actually builds all the widgets inside our window. Without this line, you'd simply get an empty window. Finally, we have the destructor. When the application closes, Qt destroys the window. Deleting the UI pointer frees the memory used by the interface. We don't manually delete every button or every label. Qt manages most child widgets automatically through its parent-child ownership system. We've talked about the architecture long enough. Let's actually build something. Our goal here for now is simple. We will create a window with a single button. When the user clicks the button, a message box will appear saying hello. And that's it. The purpose now is to see how widgets, signals, and slots fit together. It's not going to be a useful application, but it will be useful for us to understand the basic concepts. We will only need to modify the main window.cpp. Everything else that Qt Creator generated can stay exactly as it is. Qt provides a huge amount of functionality for us already. We will simply create a few objects and connect them together. Let's open the project in our Qt Creator. So in recent projects, I think it was saved as app 1. For now, let's close the app example and keep app 1 only. So here under app 1, we have once again header files and source files. You will see that main window.h is still the same. Main.cpp is also the same. We only changed the main window.cpp. You can see the code here and here is the same. Now let's run it. To run the application, just press Ctrl R. Our app appears here. If you can't press Ctrl R, just go to Build and then press Run here. And it will also create the application for it. Now, if we click on this button, then this message box appeared and it says you click the button and OK, and that's it. Now let's slow down and take a look at what actually happened here that helped us create this application. At first, we resized our main window like this. Then inside that main window, we created a Q push button. Notice that we passed this into the constructor of the Q push button. That single argument is very important. It tells Qt that the button belongs to our main window. Qt keeps track of these ownership relationships automatically, and later when the window is destroyed, Qt will also destroy every child that the main window widget owned. That's why we never have to call the delete keyword individually on each of the elements. Qt does it for us. Also here you can see we have click me as the label of this Q push button. We will talk more about that later. Next, we positioned the button using set geometry. We will improve this approach, but for our very first example, it's perfectly fine. Then we connected the button's clicked signal to our action. Whenever the user clicks the button, Qt executes the code inside our lambda. Notice that we are calling the message box here. And finally, when the main window destructor is called, it deletes the UI. This entire application only required some simple lines of code, yet we already have a functioning graphical program. That's one of the reasons why Qt has remained so popular after many years. The widget we just used is probably the most common widget in desktop applications. Q push button represents exactly what its name suggests, a clickable button. You'll see them everywhere. Save, open, delete, exit, close, wherever. Whenever the user needs to trigger an action, a push button is usually the first choice. Qt automatically handles different visual states. So, for example, the button changes appearance when the mouse moves over it. See? Then it changes again while it's being pressed. Notice when I press that button, it becomes a little darker. It can also be disabled if an action isn't currently available. Most importantly, when the user activates the button, it emits the clicked signal. Let's get back to our slide. The button itself doesn't know what click me or save or exit, what those mean. It simply announces that it was clicked. Your application decides what should happen by connecting that signal to an appropriate slot. Now, the pop-up we displayed a moment ago came from another useful Qt class called QMessageBox. Its purpose is to communicate important information to the user. Maybe an operation completed successfully, maybe an error occurred, or maybe the application wants confirmation before deleting a file. Unlike a label inside the window, a message box is a modal. That means the user must deal with it before returning to the main application. While the message box is open, the rest of the window is temporarily unavailable. Sometimes that's exactly what we need. For example, if the application asks, "Are you sure you want to delete this file?" We don't want the user interacting with other parts of the interface until they've made a decision. Qt provides several convenience functions, such as information, which is shown here. We also have warning, critical, and question, and so on. It depends on the type of message that we want to display. Now, not every widget is interactive. Sometimes we simply want to display information. That's the job of QLabel. A label can display plain text. It can also display formatted text. It can even display images using setPixMap. You'll often see labels placed beside input fields like here. So for example, we have name here and address here. Labels can also be aligned, styled, resized, just like any other widgets. They are simple, but they are one of the most frequently used widgets in almost every Qt application. Now, soon enough, our applications will need information from the user. For single line text input, Qt provides QLineEdit. This widget is commonly used for usernames, search boxes, email addresses, and many other forms of input. This one is QLineEdit. One useful feature of this QLineEdit is password mode. Instead of displaying the characters the users type, Qt can replace them with dots or asterisks or whatever. You can also provide placeholder text, such as enter your username, to guide the user before they begin typing. Just like QLineEdit, we have QTextEdit that enables us to take multi-line inputs from the user instead of single-line input. Now let's talk about QComboBox. Combo box combines a text field with a drop-down list. Instead of typing freely, the user selects one option from a predefined list. You'll encounter combo boxes everywhere, while choosing a country, while picking a language, or while choosing your theme of the software. Combo boxes are everywhere. Qt makes these combo boxes very easy to populate. We simply add items one by one, or we provide a list of strings all at once. Whenever the selected item changes, the combo box emits another signal. Let's go to the next one. Now we have QCheckbox. A checkbox is used whenever the answer to a question is simply yes or no. For example, remember my password, or let me receive email notifications, or enable dark mode, stuff like that. Unlike a push button, a checkbox has states. It stays checked until the user changes it again. You can ask Qt whether it's currently checked by calling is checked function. Some applications also use a third state called the intermediate state. Instead of being simply checked or unchecked, the box indicates that the value is only partially selected. You'll sometimes see this when selecting folders containing a mixture of checked and unchecked files. Now, sometimes a simple label or a text box isn't enough. Many applications need to display structured information using rows and columns. That's exactly what QTable widget is designed for. You can think of it as a spreadsheet built directly into your application. Each cell here can contain text, icons, or even custom widgets. You'll find table widgets like this in inventory systems, gradebooks, databases, spreadsheets, and administrative software. Qt provides functions to add rows, insert columns, and populate individual cells using the QTable widget item object. The widget also supports features like selecting rows, sorting columns, and allowing the user to edit values directly inside the table. Another very common widget is QList widget. Instead of organizing information into rows and columns, a list widget displays a simple vertical list like this. So think about a playlist inside a music player. That's a QList object. Stuff like that. Adding new items is straightforward in a QList object. We simply just call add item and that's it. If we want to know which item the user selected, Qt provides functions such as current item or current row. Removing an item is just as easy as adding an item. We simply call take item. Lists are extremely useful because many applications spend a surprising amount of time presenting collections of data to the user. So like a list of files, a to-do list, or a list of recently opened projects, stuff like that. Now, let's return to the application we built earlier. Here's our application. It works perfectly. The button appears, the message box appears, we click and everything works. But when we resize the window, the button doesn't move with the window and it even cuts off. So that's the same screenshot taken here. You can see that the button got cut off. That's because we positioned it using hard-coded values like this. These numbers never change. Qt follows them exactly. Hard-coding positions is fine for tiny demonstrations like ours, but real applications need to adapt automatically to different window sizes, screen resolutions, operating systems, and font sizes. So fortunately enough, Qt provides a much better solution. Layout managers are one of the biggest quality of life features in Qt. Instead of thinking in pixels, we simply describe how widgets should be arranged. Qt takes care of the positioning and resizing for us. The two layouts you will use the most often are QV box layout and QH box layout. A QV box layout stacks widgets vertically. That's where the V comes from. Here, one widget appears underneath another one. If the window becomes taller, Qt automatically distributes the available space. Everything stays aligned without us changing a single coordinate. QH box layout works the same way, except the widgets are placed side by side. So text boxes next to labels, stuff like that. Now let's modify our existing code and see how these layout managers actually work. I have already written the code, so let's open app 2. Now here, this one is our active project. If we want to go back to app 1, we will simply have to set app 1 as the active project, then it will work just like that. But now we want to work inside app 2. So let's see what's there. Let's check the source file and main window.cpp. Here's the new code with the layout manager implemented. Let's see what we have here. Let's just run it. Now here, the app is a little bit different. Here, as you can see, we are resizing the window, but nothing is getting placed into awkward positions like the one before. We have a label here, as we can see. Welcome to your first Qt app. Then we have say hello. It shows that you click the hello button, and then we can exit the application like this. Let's run that again. Yeah, looks just fine. Now let's dive into the code. So at first we resize the main window like this. Then we create our labels and buttons. So here we have a new Q label, new push button, and another new push button. And the label says, welcome to your first Qt app. The push button says, say hello, and another one says, exit application. And we added all of those into this main window. Also, we fixed our alignment to become align center. After that, we created QV box layout. This object will be responsible for arranging our widgets vertically. Next, instead of calling setGeometry, we simply add each widget to the layout using addWidget. We are not specifying any kind of coordinates, we are not calculating any positions, and we don't have to worry about resizing. Everything is taken care of by the layout manager automatically. Unlike a plain Q widget, a Q main window cannot directly own a layout. Instead, we create a central widget, apply the layout to it, and then tell the main window to use that widget. So that's what we are doing here. Finally, we connect the button's click signal exactly as we did before. So here we have button hello, and since we clicked it, it should pop up a Q message box with an information that will say you click the hello button. And then we will also connect the button exit with the main window being closed. Here, one important thing is that layouts only affect how the widgets are arranged. They don't change how the widgets behave. So the connect here work exactly like the previous ones. Now, let's take a look at other kinds of layouts. A vertical layout is great when everything belongs in a single column. A horizontal layout works nicely for a single row. But what if we need both? Suppose we are creating a calculator, or a seating chart, or a small dashboard with several controls arranged in rows and columns. That's where queue grid layout becomes useful. Instead of simply saying, put this widget below the previous one, we specify a row number and a column number. For example, we might place one widget in row 0, column 0, and another in row 1, column 1, just like you can see from this grid. As the window changes size, the layout adjusts while preserving the grid structure. Qt will then build the grids automatically. Now let's talk about queue form layout. The form-like structure appears so frequently that Qt provides its own dedicated class for it. So that's queue form layout. Think about any settings window that you have ever seen. On the left, there's a set of label, and on the right, there's an input field or some sort of input fields. For example, here we have name, email address, and age. And then on the other side, we have text box, pin box, stuff like that. That name is connected with the text box next to it. So that's exactly what a form layout is designed for. Instead of manually arranging every label and input pair, we simply call add row. Qt automatically aligns everything neatly into two columns. This keeps forms look consistent with very little code. Whenever you're creating a dialog where the user needs to enter information, this layout is usually the best choice. So far, even though it's nothing much, but we've built two interfaces in C++. We will be using this method because it helps us understand what's happening behind the scenes. However, writing layout code by hand can become repetitive, and once an application grows larger, it becomes way more complicated to handle everything. Qt Creator provides another option. It's called Qt Designer. Instead of writing widget placement code ourselves, we can simply drag widgets onto a design canvas. So let's see how that looks like. We will open our app 1 once again. Here, once you go to the source files, you will see that you have main.cpp, mainwindow.cpp, all of that. Also, you will have the header files, but under forms, you will see that mainwindow.ui. This is the .ui file that we actually talked about in the beginning. Here, once you go inside the .ui file, you will see that you have a design interface here. On the left side, you will see that once you open the .ui file, it automatically changed to the design tab. This is the Qt Designer that we were talking about in the slide. Here in the Edit tab, you can see that we have an XML file under the main.ui. So main.ui is actually an XML file. You can see the UI tag here. Here's our main window class. Here we have widgets, Q widget, we have a central widget. Then we have a menu bar, and then we have a status bar. This XML is nothing that we need to worry about. We can see everything from here. On the left side, you will see the widget box. Here we have layouts, spacers, buttons, then item views, item widgets, containers, input widgets like combo box, line edit, text edit, plain text edit, spin box. Then we have display widgets like label, text browser, graphics view, LCD number, progress bar, a lot of the other stuff that we need when we want to build a UI. So let's use something. You can drag and drop anything from the left side and place it on the design canvas here. Also, there's an object inspector on the right side. So here you can see that under main window, we have a central widget, a menu bar, and a status bar. So once again, if we add something from the left side, let's say radio button, you will see that we added a radio button in the central widget. That's what it's showing. Once you click on the radio button, you will see that we have selected the radio button object. By default, it's enabled. Then we can set many default values here. So like it's checkable, yes. Should we keep it checked by default? So it is checked by default. We can also change that. We can also disable it. We can also change the size. So the width can be, let's say, 50, and the height can also be 50. If there were any icons here, it would have become 50. And also you can change the text from here. Let's say hello, and there you go. You have a radio button to play with. Also, this is the menu bar on top. So just like these are also menu bar. These are also menu bar options. Here we can access different kinds of menus from all over the place. And just like that, we have a menu bar here. So let's say we want to include file, then we want to include help. Under file, we could include open file. Now let's see if there are any changes to our application. So let's just quickly rebuild and run the application. See, here we have file, and then since we didn't add anything under help, the help isn't opening, but yeah, we have open file here. The rest of the application is working smoothly. So as you can see, this file is not C++. This one is actually an XML document which is describing the structure of the interface. When the project is compiled, Qt automatically converts this XML into C++ code for us. That means we still end up with normal C++ objects. We just didn't have to write all the placement code ourselves. Many professional Qt developers build interfaces visually and then write the application logic in C++. Now let's get back to our slide. Earlier we saw this line UI setup UI this. So if we go back to our code, inside main window.cpp, we have this line inside the code. So this function reads everything stored inside main window.ui, which is this one. It creates every button, every label, every text box, every layout, whatever you build inside here. Then it attaches all those widgets to our window. So if we go back to the slide, Qt Designer also lets us create simple signal slot connections visually. So here we have open file, and now under the action editor, if we right click on it and say go to slot, Qt Creator generates the appropriate slot function for us automatically. So the kind of function that you will choose from here, it will automatically generate for us in our source code. Whether you create connections manually using Connect or visually inside this designer, it is almost always the matter of personal preference. Both approaches ultimately produce exactly the same behavior. Now, so far, you have seen that we have a menu bar on top. That's where we added our menu options here. These are our built-in interface regions. So if you look at professional desktop applications, you will notice there's much more than just central workspace. Most applications have a menu bar across the top, and many of them have a toolbar just below it, and almost all of them have a small status bar at the bottom. If we want a menu bar, we simply call this menu bar. If we want a toolbar, we call this one. If we want the status bar, we call this one. Unlike the widgets we've been placing inside layouts, these interface regions are already built into the QMain window. That means we can focus on adding functionality rather than worrying about positioning where the Q status bar should be and where the Q menu bar should be. Now let's take a look at one of the most useful classes in Qt, which is QAction. Imagine you're writing a text editor, and inside the text editor you have a save command. Where should the user find the save command? Should it be under the file menu, or should it be in the toolbar, or should it be a keyboard shortcut which is Ctrl S? Usually it's all of them. So instead of writing 3 different implementations, Qt gives us QAction. QAction represents a command. It's not a button, it's not a menu item, it's the command itself. It stores information like the display text or an optional icon or even keyboard shortcuts. Then we simply attach that same action wherever we want it to appear. The file menu can use it, the toolbar can use it, the keyboard shortcut can also trigger. No matter how the user activates the command, the exact same signal is always emitted. This keeps our code much cleaner because there's only one implementation of the action. So let's take a look at a simple QAction implementation here. As you can see, it's almost similar to how we implemented QPushButton. So at first we call the constructor QAction here, and we create a save action. Then we connect the save action, and then we use that save action under many other places like menu bar or toolbar or wherever we want to use the save action next. Now let's move to the bottom of the window, which is the status bar. Here, as you can see, this one is our status bar. Unlike a message box, the status bar doesn't interrupt the user. It simply displays useful information while the user continues working. When you save a document, you might briefly see that the file has been saved. Qt makes this very easy. So we simply just call this status bar show message, and then we can show the message directly in the status bar. Some messages disappear automatically after a few seconds. Others remain visible until another message replaces them. Here we have an important UI and user experience lesson to learn. If there's something critical, always use a queue message box. If it's simply informative, the status bar is usually the better choice because it doesn't interrupt the user's workflow. Now, earlier we displayed a simple message box. Qt actually provides many more ready-made dialog windows. For example, suppose we want the user to type a single piece of information. So instead of designing our own window, we can use Q input dialog, which is this one. If the user needs to choose a file, Qt provides Q file dialog, which is this one. This opens the operating system's native file browser, so the application immediately feels familiar to the user. Now, if you need to choose a color, then there's Q color dialog. Again, Qt already provides it. All of these dialogues share one important characteristic. They are modals. When one of these dialogues open, execution pauses until the user makes a decision. But eventually you will reach a point where the built-in dialogues aren't enough for you. So perhaps you need several text fields, maybe a few checkboxes, perhaps some validation rules, or maybe a completely custom layout. In these situations, we create our own dialog by inheriting from QDialog. The process is actually very similar to creating Q main window. We design the interface, we add the widgets, we connect the signals and slots, and then display the dialog whenever it's needed. One important function you will see is exec. Calling exec displays the dialog modally. So the application waits until the user closes the dialog. When it closes, exec returns a value indicating what happened, and that's usually either accepted or rejected. This allows our application to decide what to do next. For example, if the user presses OK, then we continue. If they press cancel, we simply stop the operation. Now let's talk about Q settings. Up until now, every application we've built has forgotten everything as soon as it closes. If you resize the window, the application forgets its size. If you choose a theme, it's gone the next time you launch the program. For many applications, that's not what we want. We would like the program to remember a few small pieces of information between the runs. And that's exactly what Q settings is designed for. Q settings stores simple key value pairs. For example, we might save the user's preferred language, whether the dark mode is enabled or not, or the size and position of the application window on the screen. One of the nicest features is that we don't need to worry about where this information is stored. Qt automatically chooses the appropriate location for each operating system. On Windows, it uses the registry. On Mac OS, it uses property list files. On Linux, it stores configuration files in the standard location. Our code looks the same regardless of the pattern. It's important to remember that Q settings is intended for small configurations data. But remember one thing, that Q settings is not a database, so it's intended for small configuration data. It's not designed for large documents or user-generated files that you will store as the settings. For those situations, we will use normal file input and output instead. So let's look at what using Q settings actually looks like. The first thing we do is create a Q settings object. Then we construct it. We provide two pieces of information. The first is the organization name, and the second one is the application name. These values uniquely identify where the settings belong. Once that's done, storing information is surprisingly simple. And when we want to read it back later, we just call the value function like this. And that's it. We don't need to do anything else. We don't need to look through the registers or the operating system specific functions. But eventually, our applications need to work with real files. Perhaps the user wants to save notes, maybe export a report, or load previously created data. For that, Qt provides two important classes. The first is QFile. QFile is responsible for opening and closing files. And then the next one is QTextStream. Once the file is open, QTextStream allows us to read and write formatted text. These two classes actually work together. QFile manages the connection to the file, and then QTextStream handles the actual text flowing through that exact connection. You'll often combine them with QFile dialog, allowing the user to choose exactly which file to open or where to save. Unlike QSettings, this approach creates ordinary files that users can copy, email, or edit themselves. Whenever you are dealing with documents or larger amount of information, this is usually the appropriate choice. So far, every interface we have created has used Qt's default appearance. There's nothing wrong with that, but eventually you will want your application to have its own visual identity. That's where Qt style sheets or QSS come in. If you've worked with web development before, the syntax will probably look familiar because it's heavily inspired by CSS. Using QSS, we can change colors, borders, fonts, spacing, and many other visual properties. Styles can also be applied to a single widget. For example, maybe just one button. Or styles can be applied to the entire application so that every widget shares the same appearance. For small demonstrations, you will often see style sheets written directly inside the code. But the larger projects usually keep their styles inside a separate .qss file. That keeps the design separate from the application logic so that both of them are easier to maintain. And then later, if you want to change the appearance, then you simply need to link one style sheet instead of another one. So here we have an example of an open source QSS. This one is styling a Windows dialog box differently. So far, every application we've seen in this lecture as examples followed exactly the same pattern. The application starts, it waits, the user clicks something, the application responds, and the application then waits again. This works perfectly for most desktop software because nothing needs to happen unless the user does something first. So for example, a calculator doesn't keep calculating by itself. A text editor doesn't keep changing your document by itself. Everything is driven by the user events. Games are different. Imagine a simple platform game. Suppose the player doesn't touch the keyboard for 5 seconds. Should everything freeze? Usually no. Enemies should continue moving, animations should continue playing, gravity should still pull the player downward, time itself continues moving. That means the application must keep updating its state continuously even when the user isn't doing anything at all. This is the major difference between a traditional GUI application and a real-time application. The program isn't waiting for user events anymore. Instead, it's updating the game world over and over again while still responding to the user input whenever it arrives. Fortunately enough, we don't need to abandon Qt's event-driven architecture. Instead, we simply introduce one additional source of events. The source is a timer. Instead of waiting for a mouse click, a timer generates events automatically at regular intervals. For example, we might ask Qt to notify us every 16 milliseconds. That gives us roughly 60 updates per second. Each time the timer expires, it emits a familiar signal. The signal is called timeout. We are still using the signals and slots here. Nothing has changed. Earlier, our signal came from a button, but now the signal comes from a timer. The programming model is exactly the same. The only difference is that the event happens automatically instead of waiting for the user. Inside the connected slot, we'll usually update our application state. Maybe we move an object, maybe we update the score, or maybe we advance an animation, stuff like that. Once that's finished, we'll ask Qt to redraw the window. The application then waits for the next timer event. This cycle repeats over and over again. So here, as you can see, we can create a game timer like this. This is our QTimer constructor. We are passing this here in the constructor. That means Qt manages its lifetime automatically. Now here we will connect the timer's timeout signal. Every time the timer expires, this function will get executed. Our function is advanced game from game widget, which will increment the star y by 4 and then call an update function. We will see that later, what the update function does. Then we will start the game time. This is all that we will need to run a game timer like this. We will never need to write a loop ourselves. Qt is generating timer events automatically. Our timer here keeps the game moving. And now we need a way for the player to interact with it. For ordinary widgets, we've mostly relied on signals and slots, but for games, things work a little bit differently. Instead of clicking buttons, the player presses keys or moves the mouse. Qt handles this through event handler functions. For keyboard input, we override key press event. This is our key press event function, and whenever the user presses a key, Qt automatically calls that function. Inside it, we can ask which key was pressed. For example, did the user press left arrow or right arrow or spacebar or whatever. Here we can see that we are asking the event which key was pressed. And if the key left was pressed, we will move the paddle like this. So this one is just the paddle x variable, but from the naming convention we could imagine that there's a paddle in a game which will move on the x-axis to the left by 20 pixels, and this one here, the paddle will move on the x-axis to the right direction. Mouse input works in exactly the same way. Qt provides functions such as mouse press event and mouse move event. A widget only receives keyboard events if it currently has keyboard focus. That's why you will often see this line inside the constructor, which is set focus policy. This tells Qt that our widget is allowed to receive keyboard input. Without it, you might press the arrow keys and wonder why absolutely nothing happens. We will use these event handlers in our game shortly. The timer will update the world continuously and the keyboard will allow the player to control it. So far, every visual element we have used has already existed. Buttons know how to draw themselves, Labels know how to display text. Text boxes already know how to look like. Games are different. If we want to display a spaceship, a paddle, or a falling star, Qt has no idea what those should look like. We have to draw them ourselves. That's exactly what QPainter is for. Whenever a widget needs to be redrawn, Qt automatically calls a special member function named paintEvent. We never call this function directly ourselves. Qt decides when the screen needs updating. Inside paintEvent, we create a QPainter object. Think of it as our drawing tool. Once the painter exists, we can draw rectangles, circles, lines, text, images, and many other shapes. When the function finishes, the painter is automatically destroyed and Qt displays everything we've drawn. There's one important rule to remember though. If your game state changes, don't call paintEvent yourself. Instead, call the update function. That tells Qt that something has changed. Please redraw this widget when you are ready. Qt then schedules a repaint at the appropriate time. Keeping those responsibilities separate makes drawing much more efficient. Now let's see an example. Here, this one is the paintEvent function that we just talked about. This is the paintEvent function that will get called by Qt automatically whenever the window needs to be redrawn. And then we create the painter object like this. Since we added this keyword here, everything we draw will now appear on this widget. Then we will fill the entire background with black like this. And then we will set the drawing color or the brush color. And then we will draw an object which will have the width and height of 20. Even though it's an ellipse, since the width and height are the same, it's gonna be a circle. And then we will change the brush color again or the drawing color again. Then we will draw a rectangle which will have a width of 100 and a height of 15, and it will be placed near the bottom. Now it's time to combine everything we've learned. Earlier we introduced QTimer, then we learned how paintEvent works and how it is responsible for drawing the current game state. Together, these form the core of almost every simple game. The timer generates regular updates, and during each update, we modify the game state. Perhaps the player moves, perhaps an enemy advances, but once the update is complete, we call the update function. That schedules another call to paintEvent. paintEvent then redraws the screen using the new positions. The timer fires again, the game state changes again, the screen is redrawn again. This cycle continues dozens of times every second. One thing I really want to highlight is that don't ever write a loop using while true. If you update the game through the while loop, it will completely block Qt's event loop. The window will freeze, the buttons will stop responding, and the operating system may even report that the application has stopped working. So instead, we let Qt remain in control. The timer generates update events. The event loop continues processing keyboard inputs, mouse events, and repaint requests. Then everything works together smoothly. This design is one of the biggest strengths of Qt. We will use exactly this approach to build our game in this section. Now, let's build something. Up to this point, we've learned several individual pieces. We know how to create a Qt application. We understand the event loop. We've seen timers in the examples. We've handled keyboard input in the examples. And we have seen how to draw our own graphics with Q Painter. Now, it's time to combine all of those ideas into one small game. The goal is very simple. A star falls from the top of the window. The player controls a paddle using the left and right arrow keys. If the paddle catches the star, the score increases. If the star reaches the bottom without being caught, it's counted as a miss. After 3 misses, the game ends. Here you will see that there's no new concept here. Everything comes directly from what we have already learned. So what we will see is how these individual building blocks work together to create something interactive. We will build this game one small step at a time. Please don't try to write the entire program at once. Just follow me. Here I'll switch over to Qt Creator. Then from the menu, I will choose File and then a new project. Here I'll select Qt Widgets application and then we will name it Catch a Falling Star. And next, now let's get back to our slide and let's see what do we have for our step 1. So here we will use QWidget instead of QMainWindow. We don't need all of the stuff that comes with QMainWindow because it's going to be a small game. The QMainWindow has menus, toolbars, and status bars. We don't need all of that. Our widget itself becomes the game. We will create a class called GameWidget, and inside it we will declare 2 special functions that we've already discussed earlier today. The first is paint event and the second is key press event. We will also add a few member variables. These variables will represent the state of our game. So for example, maybe the horizontal and vertical position of the star, then the horizontal position of the paddle, and then the player score, then the number of misses. At this moment, these are just simply variables that's going through my head, but as we go, we will declare variables as we need. Okay, now we will begin with the header file. Let's rename the header as gamewidget.h. So here, as we rename the game widget, we have seen that it got also updated. Let's just get rid of everything. We will include Q widget like this, and then we will include Q timer like this, and then we will have a game widget class just like we planned. We will have a Q object, and then this one is going to be our constructor. Since we need an explicit constructor, we will write as such, and here null pointer. Now we will create some protected functions. So here void paint event. Qt automatically calls this whenever the window needs to be redrawn. A pointer to our event and override. Then also void key press event q key event, which will also have a pointer to the event. It calls this one whenever the user presses a key. So like up arrow, down arrow, left or right, whatever. Then we will need some private slots. So void advance game. This will become our game update function, and then some private functions. So like we will use these functions as we go, but for now we will need, let's say, a void reset star, and then some variables like the current position of the falling star. So let's say star x, which will be 0 in the beginning, and then star y, which will also be 0 in the beginning, and then let's say paddle x, which will be the current horizontal position of the paddle, let's say 150, and some game statistics like integer score, which will be 0, and then integer misses, which will also be 0 in the beginning. And let's just also create a timer pointer. So these functions do not have their implementations yet. That's completely normal. We are just building the skeleton. Let's create the constructor in GameWidget.cpp. Let's get rid of all of these. Well, we will need the game widget. We will need to include that. Apart from that, let's just go with it. So here, game widget, we will have a Q widget parent, and here we will also have to define parent like this. For now, let's just keep the game window a fixed size. So let's set fixed size, which is going to be 400 by 400, let's say. We will change it later if we want. And also, I think we have mentioned this in our slide that we will set this one as well. So here, let's set focus policy, which is going to be cute, strong focus. Now that's our game widget. Let's update the main.cpp as well, since we don't have main window anymore and everything. So here the game widget header is already included. We have our Q application. Now inside the main function, we will create the Qt application like this. Let's say it's an app. Then we will create our game widget from game widget, which will be the game inside the app. And then we will show the game. After that, we will just call app.exec. Now let's try to compile it. Save all. As expected, there are some errors because we declared all of these, but we didn't define any of these. For now, we will add empty implementations so that the project builds. So here, let's say void game widget. We will define the paint event, which is going to be a Q paint event. And then similarly, we have void game widget key press event, which will have key event like this. And then what was there? Advanced game and reset star. So here void game widget once again, which will have advanced game and then game widget reset star like this. Declaring empty functions like this is a common practice in larger programs, so don't worry about it. We are just trying to see that everything builds correctly or not. Now let's try to build it. Here, since we have an empty window, I would say everything is going smoothly for now. Right now it's simply an empty 400 by 400 window. That's exactly what we expected actually. Since there's no drawing code yet, no timer yet, no keyboard handling yet, there's nothing on the screen yet. At this stage we've built only the application skeleton. Now let's get back to our slide. Step 2, we will implement paint event. Once again, remember that Qt calls this function automatically whenever the widget needs to be redrawn. Inside it, we will create a Q painter. Then we will draw 4 things to be precise. Why? We will first paint a black background. Then we will create a ball, then a paddle, and the score and misses. We will just render the scene. Now here, inside the header file, let's add our Q painter, and then we will also include Q key event. Now let's implement this one, which is gonna be our paint event. Here we will create the painter object that will draw on this widget. So Q painter, and we will pass this as we explained before, or else it won't know that we want to draw inside this widget. So that's why we are passing this. And then we will call fill rect, and inside it we will just paint it with black. After that, we want to draw the falling star, which will look something like this. And also, let's see the paddle, it will look something like this. This one is yellow and this one is cyan. So here, at first, we will set the color of the brush. So painter dot set brush. Here we have to say we want to put yellow. Later we will also need the color cyan. But after we set the brush to yellow, we will draw an ellipse. Painter dot draw ellipse. And here we will say the position first. So these are the positions. Here, zoom in quickly. Okay, there we go. Then the width and height are gonna be 20. After that, we set the brush color to cyan, and then we will draw a rectangle. And then we will go for paddle X, and then we will get the height of the container, and we will subtract 30 from the height, and then the width of the paddle is gonna be 100 and the height is gonna be 15. Now we will draw the score text, which will be painter dot set pen, And here our color needs to be declared, which will be white. Now we will draw text, and as always we need to define the position first, which is roughly there. Let's set there, and then we will pass a Q string, which will put the score there and misses there. Now in this Q string we will pass the arguments like this. Okay, I missed a column right there, and now everything looks fine. That's, I think, all the drawing that we need to do. So if we run the program, nice. Here we can see that we have our yellow ball here, and here we have our paddle here, and the score and misses. Notice that if we move the position of the star X, so let's say the width of our window is 400. So if we set it to 200, it will be roughly at the middle. Not entirely, but roughly at the middle. We will add it. Now let's run it. So yeah, roughly in the middle. So here, as you can see, we have our yellow star and our paddle and score and misses. Now let's get back to our slide. So we need to add motion. At this moment, we just painted the objects. It doesn't move, it doesn't do anything. But as you have seen, I have shown you that if we increase the X position of the star, it moves. So we need to move it constantly according to our game loop and according to our game algorithm. So you can get the idea. Currently we have our star Y set to 0. Now what if we add 10 to it? Let's run the program. Notice that it's moving from there. Let's say we add another 10 to that like this, and let's run it. It moved a little. So let's add another 10 to that. Let's copy it like this, and then keep running. Save all. Let's repeat it once again. Save, run. Yeah, it's moving. Let's just move it by 200 pixels, let's say. Now let's run it. Yeah, it's way down below now. You get the idea. What we will need to do now is to update everything in a game loop or some kind of a loop that we just discussed. Let's get back to our slide. What we need is the queue timer. Instead of updating the code like that or clicking a button to update entire widget, the timer will generate events automatically about 60 times per second. Each time the timer fires, we will update the game state and ask Qt to repaint the widget. This gives us continuous animation while still allowing Qt's event loop to handle keyboard input and window events. So let's build that now. At first, let's update our constructor because we need to position the star first. So we need to call reset star at the very beginning of our game. In order for the reset star to work, we will need a random generator function. So we will include Q random generator. Using this, we will randomly position the star on the screen so that it gets positioned randomly on the x-axis while being still at the top. Now, let's get back to our source code and create the game timer. So timer will be new queue timer, and it will work on this widget only. And we have our advanced game function, which is supposed to update the game loop. So every timeout will call the advanced game function. So connect our timer with queue timer timeout, and it will work on this widget, which will have the game widget's advanced game function. So we connected the timer's timeout with advanced game function. So now we will update the timer about 60 times every second, which will be roughly 1600 milliseconds. Now let's implement reset star because we are calling the reset star first. At first, we will need to choose a random horizontal position. Here, our star x will be queue random generator, and global, it will be bounded within, let's say, 380. Since the width of our application is 400, if we bound it within 380, it will stay within the range of our application. Then, since we are resetting the star will always start at the very top. And now we will update our game update function. Since we didn't write anything, let's start by writing that we will move the star downward every frame. So star y will go by, let's say, 4 pixels. And if the star has left the window, we simply restart it for now. So if the star position is greater than the height of our widget, then we will simply reset the star. And then we will ask Qt to repaint our widget. The update function is really short. As you can see, our logic is also very short, and I believe this will work. Let's run the program. Yes, save all. So yeah, the star is falling. The score isn't getting updated because we didn't write the logic for it, but the star is falling every time we are going through that loop. It's not the loop, but it's the game loop actually. You get the point. So now let's get back to our slide. Here we will set our input, our collision, and our scoring events. Now we will add the final pieces. The player needs to move the paddle. We will do that by implementing key press event. Whenever the user presses left or right arrow key, we will move the paddle by 20 pixels. We will also make sure it never leaves the game window. Next comes the collision detection. Every time the star reaches the same vertical level as the paddle, we will check whether their horizontal positions overlap or not. If they do, the player catches the star and earns 1 point. Otherwise, it will miss the star and it will count as a missed one. After 3 misses, the game will simply end, and instead of continuing forever, We will stop the timer and display the player's final score in a message box. These will need additional changes to paint event. We will look into that. And now, so let's start with the first one, which is let's work with the keyboard input. Here, let's implement this function. If we move left, we want the paddle to move left. So when we are checking for events, if the key event is a left arrow key, which is Qt the left, we will move the paddle. Paddle X will become paddle X minus 20. But since we need to keep the paddle within the window, so we will have to make sure that it doesn't cross 0, which is if we keep subtracting 20, 20, 20, 20, then the paddle might go from 40, 20, 0, minus 20, minus 40, minus 60. We will need to restrict that so that it doesn't go beyond our window. So now Qmax is going to be 0, this. So it won't have to go beyond the screen. Also, I think I missed an event here. Also, the same one for the right key. Let's just do it manually so that you can also learn from it. We will look for key events like this, and we will check if it's equal to key right in this case. We missed an arrow here. Now we will do the same thing here. So paddle X will be equals to paddle X plus 20. But since we will have to limit the paddle so that it doesn't go beyond our screen, here as you can see, this is the position of the paddle, this leftmost corner. So if the width is 100, which it actually is, the width is 100. If we position the paddle at 400 in the x-axis, this paddle will go beyond the screen, which is it will go beyond the widget. We don't want that, so we need to limit that exact position to 300 so that the paddle doesn't go beyond our widget. So what we need to implement is that we need to make sure it doesn't go beyond 300. This time we will have to get the minimum, and we will get the minimum of these two, whichever's lower. And every time we press the key, we want our screen to get redrawn immediately. So we will call the update function here. And now we will replace our temporary advanced game here because we want our advanced game to react with key press events, scores, timers, misses, and everything. Here we will keep moving our falling star, and then we will check if the falling star has reached the paddle. So here we will check if star y is greater than or equals to height minus 35. Why 35? Here our paddle's height is 15 and our ball height is 20, which is not the ball, it's the star. So here our paddle height is 15 and our star height is 20. So combine that, we want to check if the star y has reached the height minus 35. Now we will check if the star overlaps. Since we just checked if our star overlaps vertically, now we will check if the star overlaps horizontally with the paddle. So let's declare a boolean named caught, and inside the boolean we will check if our star x plus 20 is greater than or equals to our paddle x, and we will see that if our star x is also less than equals to our paddle x plus 100. And now if caught, we will increase the score plus plus. Else, we will assume that the player has missed, so we will increase the misses count. Here we will check if the misses is still greater than 3 or not. If it's greater than 3, we will stop the timer. I don't like the gaps here. So we will stop the timer and we will show a message in the message box. Information. We haven't included message box yet, so that's why we are getting the error. We will fix it shortly. For now, let's clear up this one. So it will be linked with this and it will say game over. And then it will show the final score, which is convenient for us. And then we will pass the score as an argument. Since we have checked that it has reached the paddle here, so after checking that, we will reset the star there. Now we will just copy or cut this one and reset the star like this, and then simply update the game. I think that's it. We have just completed the game code. Well, we will need to include the queue message box. So let's go here and include the queue message box. I think that will get rid of our queue message box error. Now let's run it. So yay, I think our game is working. Yeah. Ah, yeah, yeah. Ah, let's not miss that. I don't know why am I playing. Never gets old. So yeah, let's just miss it for now. One miss, two miss, and then we will catch the star again. And then we will intentionally miss the last one. So yeah, it shows the final score. Let's say okay. I think our goal is met. Here everything updates smoothly and our game works perfectly. It's only around 78 lines of code here, and this doesn't count actually, and this doesn't count that much either. So within just 78 lines of code or less, we got the thing up and running. Now, let's take a moment and take a closer look at what we did with the math. So here you can see that it calculates the horizontal position of the star and the paddle overlap. The math is explained here. I have created this slide for you so that you clearly see what's going on. Then we check the caught variable. If the caught variable is true, we increment the score. If it's not true, we increment the misses. And that's it for the collision detection. So what I told you about the left cornermost edge of our paddle, it's explained right here. Whenever you revise this entire lecture or review the lecture, it gets easier for you to remember how it's done. Now, let's take a moment to appreciate what we just did in this lecture. We started with an empty Qt widgets project. Then we created our own widget by inheriting QWidget. Then we learned how to draw graphics using QPainter. Then we animated those graphics using QTimer. Then we responded to keyboard input with key press event. Then we kept track of the game state using ordinary member variables. And finally, we combined everything together to build a complete and interactive program. So here, every one of these pieces are really important. The game isn't introducing completely new ideas. It's just implementing what we actually did. And we built the entire game step by step, just how the real software is actually built by combining many simple concepts rather than relying on complicated tricks. Now, this small game is just the beginning. There are many ways you could improve it, and the exercise of this topic is to improve the game and refactor the code. So you could add multiple falling stars and whatnot. Just follow the instructions there. Now let's finish by looking back at everything we just covered today. We started with the idea of graphical user interfaces and saw how they differ from traditional console programs. We introduced Qt and learned about its event-driven programming model. We explored widgets, layouts, signals and slots. Then we built our first graphical application. After that, we learned about menus, actions, dialogues, settings, and file handling. And then we built a real game. In Qt, every single idea is generated from the same thing again and again. It's the same ideas that appear everywhere. Signals and slots connect objects. The event loop keeps the application responsive. Widgets display information. Events trigger behavior. And once every one of these concepts become familiar, learning the rest of Qt becomes much easier. From here, there are plenty of directions that you can explore. You can build larger desktop applications. You can create more advanced games. And you can work with networking, databases, multimedia, OpenGL, or even move into Qt Quick and QML for modern user interfaces. The important thing in this area is to keep building projects. Read the documentations as always. Here's the link to the documentation. Watch lectures, watch tutorials. You will be able to explore tutorials from here. Let's close the project. Here you will see tons of examples. So it's in the Welcome tab and then the Examples tab. There are a lot of tutorials that you could get started with, and also there are courses. But I think we have a fair enough overview of how to handle Qt and how to build basic applications. Watching those courses or following those tutorials or even watching this lecture again and again is useful, but writing code is where everything really starts to click. So play with Qt and play with the interfaces, play with how the things are moving in here, and I hope you will eventually get along with Qt programming and the entire Qt framework. So thank you for following along today. I hope everything goes well for you. I'll see you around. Bye bye.